Okay, let's line you up a little bit better. Right, this is a quick one. It's work solution 6. I'm going to go over what is in the course notes. I have to confess, I don't entirely like the question, the way it's structured in the course notes. Not really the sort of approach that you would see in an exam. But nonetheless, so that we can tick this off and you can have a video of that particular solution. Let's go for it. So some of the good stuff is that we start off with what stress is. So stress is going to be force divided by area. And this is an example where we depart from an exam question, because normally exam questions, they don't want you to find the area for the cross-sectional beam, they want you to find the diameter. So you would use that instead of area in an exam situation. So what stress are we using here, what force we're using here, should mention that. So the force, if you imagine we got the beam and you've done maybe your method of joints on this beam and you've found we're going to call this A, B and C. So you found the internal force in BC. Let's say we've got a load being applied up here, and so that force is going to be related to the internal force BC, okay, that you're looking inside that beam. So it's internal forces we're interested in. And the stress, what does that come from? Well, that will come from a customer's specification. It might come from a customer specification in terms of the factor of safety the customer wants, or it might come from, we just tell you, I want no more than 100 megapascals in my beam, please. Okay, so everything works in terms of stress, in terms of the structural integrity of our framework. So that's why we're rearranging this. So we would know what the internal force is. In a way, that's kind of fixed, dependent upon the load. We would know how much stress we're going to apply one way or the other, either being told directly or using a factor of safety. And from that, we would probably then decide what size bar to order in terms of its diameter. So that's the basic setup of the question. So we'll use stress is force divided by area. We rearrange it to find that to find the area that we're looking for. So in this particular example, they use a factor of safety approach. The factor of safety approach is based upon the ultimate tensile stress, well, that's the ultimate tensile stress divided by the axial stress. So if you imagine that you've got a plot of you need to do a stress strain plot, and stress strain plots will go nice and straight up to roughly where the yield strength is, so that's YS, and then they go up and they kind of curve around, and the peak, so that's higher stress that the beam can actually take, and that is the UTS, the ultimate tensile stress, also known as the ultimate tensile strength. Okay, so that's the highest value that I can have. And how we define factors of safety is that we're going to take that big number, UTS, and then we're going to decide on how high up this plot we're going to go. So let's say we're going here, so roughly going to go here. So that's the actual stress I'm applying. So you can see the factor of safety is going to be, I don't know what this is, but you can see that you've got you're always going to end up with something, let's say, of order 2. You know, it's certainly going to be 1.5 plus-ish for most structures. So those are the numbers that you're looking for. So you're looking for a factor of safety that's bigger than 1, always. If you don't get that, then your whole thing is going to collapse on you straight away. So Let's come back to this equation here. So we have found from our method of joints or method of sections analysis what the internal force is. Okay. Now we're going to use this equation here to find out what the actual stress that we're going to have in the beam. So we're finding out this term here. So the actual stress is, we're going to rearrange this formula here. So remember that formula there needs to be always bigger than 1. We'll rearrange that so that we find actual stress based upon the material's ultimate tensile stress divided by its factor of safety. So it's going to be less than the ultimate tensile stress, because factor of safety will be bigger than 1. So the customer in this particular case has asked for a factor of safety of 2.5. We've been given in the question how much ultimate tensile stress there is, and it turns out to be 200 megapascals. So 200 megapascals divided by 80, divided by 200 megapascals divided by 2.5 leaves me with 80 megapascals. So I've now got, my throat's going, now got this value here, which I can now put in. And again, I'll remind you, this is the internal force. We would have found that from the method of joints or the method of sections. And now we've found the stress that we want to have in the beam. So put those two things together and we can find the area of the beam that we require. So it turns out, we're going to imagine that previously we've calculated this from a method of sections or method of joints type analysis, and now I've put in the amount of stress that I'm going to have, and now I'm going to find my area. So I've got my area there. So normally in an exam situation we would take that area and then we'd go on to find the diameter. Now let's say, just for example, actually let's find out what this diameter is. So 9.896 to the minus 4. So times that by 4, divide it by pi, and then square root it, and times that by 1,000. So that gives me a diameter of 35.49 millimeters. So what do you think we would order in terms of the diameter of the beam? Well, normally with numbers we round them down, so we normally would go, oh, I need 35 millimeters. That's probably not British standard, by the way, but we'd probably say, oh, round the number down, and that would be the wrong thing to do, because we need to make sure that the stress in the beam is going to be a bit below 80, not a little bit above. Make your beam a little bit thinner, and then you're going to increase the stress, so it's going to go above this 80, which is beyond what the customer is specifying. So we need to probably order a diameter of 36, because we would probably be working in units of millimeters. Okay, and that would be true even if I had, say, 35.01. Okay, to about 5-6 figs. So if I had any value there, I would still be rounding it up to the 36, even though you think, oh, that's so close to 35. Go on, choose 35. If you've got a little bit more than 35, you would go to the 36. At least on the bridges that I drive over. Okay. So I can rewrite this in terms of meters squared as millimeters squared. So to do that, I would multiply it by 1,000 and then 1,000 again. Okay, because we got meters squared. So 1 meter equals 1,000 millimeters, but I've got it squared, so we have to do it twice. Now this is where the worked example again differs from a typical exam problem. So first of all, we start off with normal stuff. So we've got Young's modulus, or the modulus of elasticity, whatever you want to call it. That's the E number. Is the stress divided by the strain. And normally the stress that we'd put in there would be the stress that's being experienced inside the beam. And that's how normally we do an exam question. But in this particular case, we are being given the stress that we're going to use. So that's the value there. So we've just been told what to use there. So we're going to rearrange this equation to find the strain. And for your strain in an exam, if you're not getting 1 times 10 to the minus 3, 1 times 10 to the minus 4, or 1 times 10 to the minus 5, those are the typical kind of strain values that you're looking for. Or if you want to think about it in terms of micro strain, then sort of like 10, 100, maybe 1,000. So those kind of values we would normally expect a structure to be experiencing. So in this particular case, we're getting 1 times 10 to the minus 3. So it's bang in the kind of traditional sort of value I'd expect to find in a structure. So remember that this is dimensionless. Normally we work in microstrains, so this could be rewritten, this could be rewritten as epsilon is 1,000, either just with a micro or micro epsilon, or 1,000 micro strain. Okay, so 1 times 10 to the minus 3 could mean this. So you could have a question looking a bit like that, where the mu is representing 1 times 10 to the minus 6, or emphasizing the fact that I'm working in micro strain, using symbols or using words. So all these things are the same value. So once we've got the strain, we can then go on and work out what the change in length is going to be. So that's simply rearranging the strain formula, elongation divided by the original length. So rearrange this to find the extension. And then we've got microstrain times the length of the bar, and then that will give me the change in length. So normally I would present answers 10 to the minus 3 in millimeters, and we're going to do that here. So that's our final answer to the work solution 6. As I said, that's a little bit different to what you'd expect to find in an exam paper, but the equations you're using and the principles that you're using in that work solution are the same.